Afternoon. You guys can hear me?
Yes,
Yes, Doctor.
Okay, I'm going to start to record this session so that you can review later. Huh? All right.
This call is now being recorded.
Okay, so how you guys doing? You guys ready for the final exam of this EIM? Ready or not?
Yes, Doctor.
Hopefully everything's okay. Huh? Right, as promised, so we're going to do a review class. Each lecture will provide you 1 hour review class. So me start today, then following by Tena, and then probably, I don't know, Dr. Ilman will do so. Okay, for me, as I mentioned, so I will do the exercise question that I given to you the last lecture. I think you all have that exercise sheet, right? So you can open up for the exercise number 4, the one that I give you later, and then the exercise question, exercise 2. So the one that I discussed, the question number 1, and then question 2, I leave it to you to do. Okay, but first, I will go over the exercise 4, which is given later in the e-learning, and then I will discuss with you on that. Okay, because this is with regard the ADC also. So I think we'll cover by the Tena. Anyway, we just go a bit review on this electronic instrumentation and measurement. Okay. So let me share you the page, the exercise 4, so that you can actually pull up your copy also and see. You can do it together on this. Okay, this is exercise 4. Can you see or not?
Boleh, Doctor.
Okay, do you have the same copy? I think you have the same copy. So this one with answer. So I'll provide to you later on, but now I think we discuss first. Okay. Before we start with this one, I would like to recall of your knowledge, perhaps, on the instrumentation. So the first block diagram that you have learned in the instrumentation, what is this? Then we go to the second block, right? And then the following block. Can remember the first block. Yes, transducer. Or simply we call it sensors, right? So sensors produce signal, electrical signal, which is somehow, sometimes it comes in very small value, and sometimes it is full of noise. Okay, so we have to handle that. So it's come to the next block. So the next block is what? Yeah, we do the signal conditioning. Okay, once we have a proper signal, but still in analog, so computer or electronic system cannot still understand it. So we got to do something else so that the computer will understand it. So what is the next block? Yeah, everyone is good. ADC or analog to digital conversion. So now we have everything is in digital. So what is this? This block. The next block is what? Once we have converted all the signal into the digital. So what is this? Anyone can guess or can tell me? Yeah, processor or computer lah. Okay, or any kind of computation mean. For example, embedded system, microcontroller, microprocessor, kind of. Okay, jadi we have everything inside. We understand the digital, and then we can process that signal into a meaningful one. For example, we have in the density and so on. So that's what computers are. Okay, so now you have the value. For example, temperature, right? Temperature, we have some value, range of value, right? The correct and calibrated temperature. Then what do you do next? If you want to do next, so a few things you can do next. Okay, few things you can do. Okay, first one, I show you very basic one, just display, right now. Display the value, whatever we're reading, so we can display it in digital form so that we can understand what the value is. For example, temperature, if now is 30 degrees Celsius, so you put it onto 30 degrees Celsius. If the user wants it in Fahrenheit, so you have to change the value into Fahrenheit and then display in Fahrenheit. What is the next thing to do that you can do? And then another thing probably you can do. I would suggest that probably we can save or to record the data, right? Record the data so that you can do extensive analysis after that. Okay, probably you have to put in some advanced software or kind of thing, so you can put it there to study the trend or whatever it is, or record for future use. Agree with me or not? Okay. So next things I would like to discuss. So next thing that you can do besides these two. This is the data that you have gathered. You have starting from the transducer, you condition the signal, you convert to digital, and then you process it through the computer, and then now you have the reading. Take example, temperature just now. So what you can do? What you can do? This is important. So you remember the word control. What about control? Yeah, we have actuator, then we can control through the actuator. Good. Example, we're talking about temperature now, right? So if the room is actually, you want to control the room within 22 to 25 degrees, 20 to 25 degrees Celsius. So you get, you measure from the sensor, you get the value, the temperature. So in order to control the room temperature, so you've got to have a actuator, right? actuator, for example, you can turn on a fan, turn on and off, fan, so that you get the temperature control. Or probably you can turn on aircon, right? Aircon, turn on or off aircon. So that's what you do. So when the room is, controlled by this fan or aircon, so if it's hot, the aircon will be turned on. So when the transducer read back the temperature, so it get colder than the specified, and then you can control the fan again to turn it off. Okay. There are some mean of control. Also, this one most of the time, this one is just digital control. Can turn on a relay or whatever lah. But sometimes you also can use the ADC as a control. This one that we found a lot in our mini project Viva the other day. So we are misunderstand about ADC. Okay, if you are using ADC, so you got to use the same as what ADC here lah. From the computer, we have to control the ADC. Then ADC will output voltage, which is the one that can control, for example, light. Okay, so this light you can make it bright or dim lah, in order to control the brightness of the. Okay, somebody noticed it's not ADC, it is digital to analog converter. Okay, but this one has to control by the computer directly, and then this one will control the light here, so that it can be dim or it can be bright, so that to control the room intensity, light intensity, or to compensate the situation inside the room. Okay, those are the things. So you can understand that this one is the very general understanding about the equipment there, electronic equipment here, which is you can measure the parameter and then you can control the parameter so by using this concept. All right. Any question about this? Any disagreement about the one I mentioned here? Okay. All right. So I'm going to leave this out. So we're going to start doing our part here, which is only this. I will cover today for this thing only. Perhaps we get something from a signal condition. Okay, but this one is the focus. Right. Okay. So I'm going to leave this out. And we'll do the exercise then, the one that I give in the e-learning. If you don't have that one, you can download from the e-learning right away. So it is available. So you can see the question, but without the answer. So now we'll be discussing the answer. If you have any question, you can ask straight away. Don't wait, because I'm going to spend only 1 hour with you, and that's it. Then you'll be ready for the final exam. Okay, the first question. Describe the two important factor in analog to digital converter. Factor. So the answer is basically sampling and quantization. Very important. You have to do the sampling and then quantization. Sampling is how fast you sample the reading, okay, and then the quantization is to convert that value, that use the sample value into a digital form. So this is important because we want to make the process, the conversion process, maintain the information from the signal as much as we can. Okay. For example, the input signal like this, when we do the ADC, we should get like this also, not like that. I think you can read from the slide. So all this is already described. Okay, so we want the actual signal come out from the ADC, our ADC. So this amplitude also is important, is accurate, same as like this. Okay, all right. So that is the two important thing of the ADC. Beside this is the resolution lah. Resolution, I think resolution you have to understand also. In order to get the actual signal like this, so we have to have enough resolution, which is involved in this quantization lah. Okay. Question number 2. Any question on question number 1? Okay, question number 2. Design 3-bit successive approximation ADC and flash ADC and compare these two types of the ADC. So I think this one also, if I don't really teach you this one, I'm not sure whether Dr. Tena has teach you, but this one is available on the slide, so you can read it. If the successive approximation or SAR, so the configuration is like this. So this is the comparator where you feed in your signal from the sensor. Then we connect to this DAC in the converter, and then this is the SAR module. So we can give a signal start conversion and then end of conversion. So this will do the conversion. Then the result will coming out from the output of this ADC of if it's 3-bit, only 3-bit output, 3-bit. If 4-bit or 8-bit or 10-bit or 12-bit, so going to be the output. Okay, how the operation is like this. We have a signal for start of conversion. We have the signal of end of conversion, and then we have clock for every time. Clock every time to start the process. Okay, start the process of the conversion. So this is a signal that involved in this SAR. Okay, if you can see from here, the first clock is actually start with the most significant first, because there's 3 bits. So check whether that 1 bit is 1 or 0. And second, go to the D1. Significant bit first. And then, okay, the process is for this kind of question, if there is a question like this, so you have to write like this one. Start with a output code, yes, register for the output code. So you have initialization 0, so this is 0, right? And then we start the conversion and start clocking it. What is the output here? What is the output here? This is just a comparison. This must be greater than 0, right? It's not negative, right? So therefore, that's the way it is compared. So whether VD is greater than V in, yes, yes. So this one is considered 0 for the bit 0, while if less than V in, if VD less than V in, so we consider this one and we maintain this n. The first bit is 1. Okay, the first bit is 1. So that's the first step. Either it is greater or less than V in, the VD. So you put VD here, right? Okay, and then go on to the next. So you compare also, but if you only one way to go lah, right? So if it case of the VD is greater than VN, the first, so you're going to look on the second bit, then compare this one. Same thing goes, and then it will result in this option, the result, all of this option. Okay, right. So there you go. You have the output code for the 3-bit of ADC, what you call it as AR ADC. This is the first clock, and then second clock, and then this is the third clock. Then you get the result, either one of this 1, 2, 3, 4, 5, 6, 7, 8. Result will be like that. So if you have more bits, so a lot of clock required basically to process every bit. Okay, that's it. Any question? If any doubt about this, or I will give this answer for you to analyze. No? So what that way it is to calculate. Okay, that is SAR. If you have a flash type of ADC, 3-bit also, talking about 3-bit. This one is fastest. So this is the fastest ADC type, no? Which is you just hook the wire, hook the input signal to the comparator. So when you hit it, there is no need for clock, but it got the result straight away. This is still compare, no? But if you talk about resolution, but the 3-bit require 1, 2, 3, 4, 5, 6, 7, 8, and only X comparator. Kalau you have more bits, so there will be more comparator, so that you can get the resolution required. So, but it is very fast. See, like this also, but this is connected to every single comparator that compares the values that's specified here. The value of V1, V2 is decided by this, like this. V reference divided by 8, and then V reference divided by 4, and by 8, by 3, 8, half, 5 to the 8, 3, 4, and then 7 to 8. So you get the value, and then you put the reference. Okay, so the V in include here, and then your reference is like this. This is reference voltage. You do this is the voltage division only. You get this value. So if you want to get this value, you have to sum up or you calculate the correct R value so that you get this proportion of the voltage reference. Okay, when you put in the V in here, this V in here, then you get the result already, and then inside this what we call priority encoder. So the result will be coming out from this output 3 bits. And then the solution is like that. Like this. If the value, because this one, the result here will be either 0 or 1 as you compare it. So if it's 0, 0, so the value of D2, D0 until D2 is 0. And 0, 0, 1, the value of D0 is 1, and then the rest is 0. And so on, like this. All the possible value for the 8-bit here, and then you get the result of the 3-bit output digital. This is a converted value. Okay, that is a flash ADC. Understand? Faham? You can go back and check lah. But this is it's a fundamental calculation, fundamental to understand what is the flash ADC and also what is the successive approximation ADC or SAR. Okay, I want to ask you, comparing to these two ADC type, which one you see is fast to use and then suitable for the fast application using these two? Which one is suitable for the fast application? Whichever you need to convert the signal very fast. So of course you need a flash one, right? Okay. In other way, I ask you also the next question: which one is complex compared to these two type of the ADC? Which one is simple? Which one is complex? Someone say that a flash is complex. I will agree on that because if you think about if you want to wire up, right? Wire up. How many wire compared to the SAW one? I think SAW has less wire, right? Is kalau tengok flash ADC ni a lot of wire to connect. So I believe this is more complex, huh? Okay. So complex mean what? Complex mean what? You have a complicated. So you have a lot of component also inside here to buy, to put in. So I would agree that flash is more complex and simpler is the SAW. Okay. Right. So in terms of cost, what do you think? Which one is expensive? Yeah, true. True. And then because you said more complex because this one is inside, so the probably is complex from the architecture. This one is simpler in terms of architecture. But component-wise, is this one is more complex. We have a lot of comparator to put in. Okay, so in terms of cost, which one you think this is cheap? Yeah, I agree on that. I think SAW is cheap. In a way, yes. Somehow this flash also can be cheap because it's only comparator, right? But if we are talking about we want to get higher resolution, we want to get more accurate. So what do you think that this flash will require? So it will require a lot of component, right? So this one will get more expensive then. Okay, so enough of that. Just for thinking. So probably the question probably ask you about that. So you can think of anything. It's logic to explain on that. Okay. So move on to the next question, part one. Ini so it's also asked about the complexity. ADC, flash ADC require many of M component that leads to higher power consumption, costly and more complex design. So this is the answer. When you have the power consumption is high because of many components, so you have to buy also costly, a lot of component and more complex design. Okay, go on to the third question. Describe a multiple channel data acquisition system. We have our appropriate block diagram. So this example, if you have many transducers, like this example shows we have 4 transducers, and then transducer probably give you a different type of signal, so that you require a specific signal conditioning. So you have signal conditioning 1, 2, 3, 4 each for the individual of the transducer, and then you come to the multiplexer because this one is the key component, so the ADC. So you don't want to waste on this ADC capacity. So you come to the multiplexer so that you can multiplex the output from the signal conditioning to the ADC in sequence, right? So that you can use only one ADC. You don't have to supply ADC for every signal conditioning circuit here. So this is the way you do the multiple channel data acquisition. So a multiplexer means that you allow this one to go in first, and then you do the ADC conversion and get to the processor save it, and then after that you allow the second one, okay, and then make the conversion, then put into the processor save it, and then you allow the third one, okay, and then the fourth one, and so on. And then you can repeat back here, then repeat again. So that is the purpose of the multiplexer. Okay, all right. Want to get the value inside the processor, you can do whatever display or processing. So this multiplexer very fast. You can multiplex it very fast. So you don't have to worry about the delay. Okay. But the system, the whole system has to be in sync. This ADC must be fast enough. This multiplexer also fast, so that you can get every data in even you're not realizing it, you're measuring 4 transducers at one time. Okay, so this is the answer for the multiple channel data acquisition system. Okay, go on to the next question. Question number 4 here. This is a bit calculation oriented. I think this should be familiar with. You all should be familiar with. The question asks about the light sensor that produces 0.1 volt at 10 lux. Okay, 0.1 volt is 10 lux, 2.3 is at 1000 lux. So but still you see that this is not starting at 0, so straight away you know that this one has to be used, the signal condition has to be using differential amplifier, right? Okay, so the task is design a suitable signal conditioning circuit if the sensor will be connected to the ADC with 8 volt reference voltage. So remember the ADC is 8 volt reference voltage. So the suitable amplifier, of course, as we mentioned just now, differential amplifier is the suitable one because we want to make full use of the ADC resolution. So we got to start at the 0.1, we are offset to 0.1, and then go straight to the 2.3 volt. So all this conversion from 0.1 to 2.3 volt will be using the ADC resolution. Okay. So the circuit is like this. So you have to set this V1 referring to the offset voltage, which is decided in 0.1 volts. You have to make sure V1 output here equal to 0.1 volt, right? Then V sensor will go into the second lead, which is on the non-inverting terminal here, right? And then we get the output, which is this one also calculated with the gain. Okay, with the gain RF over RI is we're going to get the gain. So since the ADC ref is 8 volt, assume that Vmax is 8 volt. So Vmax must be 8 volt lah. So Vmax must be 8 volt, and V sensor maximum is 2.3, and V signal minimum of the sensor is 0.1. Okay, so formula very simple. V out equal to V2 minus V1, RF or RI. This one is a gain, but this one is the different voltage between the input and also the offset voltage. Right, V1 is the offset voltage, V2 is the voltage of the sensor. So you can calculate this one for the maximum voltage reference 8 volt, and then maximum on the range, and also range here to range of the input signal 2.3 minus 0.1, so you get 3.64, and then equal to RF over RI. So from this one you can calculate the gain because this is RF over RI is equal to gain. Okay, but you just need to specify what's the value of the RI and RF. Okay, RF is R feedback, R input is Ri. So if you assume 10K, so you get this value from the Ri. Okay. In order to configure this V1 or the minimum voltage ataupun offset here, so you got to do some calculation to determine what the value R1 and R2 in your voltage divider circuit, right? So VR for sure we want to be 0.1 volt, okay, and then R2 over R1 plus R2 time the voltage reference, whatever voltage reference you put in here now is 5 volts, so just 5 volt. Okay, voltage supply, this voltage supply for this voltage divider, 5 volt. So you can assume R1 and R2 with a correct value, so you can find this R1, R2 value. For example, this one I assume R2 is 10K, so R1 will be 49K. So this assumption has to be good enough so that you can get a value of R which is available in the market. So you don't want to get some value that is a weird value which is you cannot find it in the market, right? Okay, that's it. I think this is very normal. You have to do this calculation all again and again until you get familiar, and then you have no problem on calculating this differential amplifier, the gain, and so on. Right? So a lot of exercise given by Dr. Tena also, you can do it again and again. So this is repeatedly like this. Okay. Any question about this? No? So we go on to the next one. Determine the ADC output for 10 lux. So when the ADC, we want to know the ADC output. ADC output, not the signal conditioning output. So ADC output. So now ADC 10 lux is equal to 0.1. Okay. ADC output is basically 0.1 minus 0.1 times 3.64, then equal to 0. Right, kalau because the offset is 0.1 and then it says 10 lux. So if 0 volt at the ADC, so it will be equal to this 10 lux. So we offset, right? So this is ADC output, 0. So if 1000 volt, 1000 lux, and the output sensor is equal to 2.3 volt. So 2.3 volt minus the offset, 2.3 minus 0.1 times the 3.64 and then equal to 8 volt. So it's 1000 lux. So the VADC will be equal to 8 volt, which is the maximum one. That makes sense, right? Okay. Right. But if 100 lux, you have to use linear equation. This is one of the way to use linear equation to get the get the 100 lux, because it's supposed to be linearly changed. Okay, you have to calculate the using the y equal to mx equal to c, and then you will calculate the m's and also c, and then after that you can get the value of the output, which is equal to this. And then you get the 0.72, then you want to calculate in terms of digital, so you can use this formula. Okay, that's it. Any question? 240 lah. Right, by referring to figure 1 and figure 1b, calculate the necessary output voltage of DAC. You want to go over this one? It's not important because I don't think this one is actually will be any kind of question like this in the final exam probably. Because I want to straight away go to the exercise question number 2. Okay, I think you can go over by yourself, can or not? This one. Because the answer is here. And then this flow chart, if the question asks See, the question is which question asked for the one. Okay, so you are trying to get the DAC so that you can turn on this light accordingly, so that you get the actual lux, no? So like that. So this is a comparison. Perhaps maybe you can discuss a bit on this comparison lah. So last time when you do the mini project, you do the flowchart. So in computer it's sequential. You cannot compare everything in one one block. For example, this one we have a 3 level here, 3 or 4 level here. So first you compare X with 10 lakh, X with 100 lakh, X with 1000 lakh, right? So if greater than 10, so you go to check next, okay, whether it is greater than 100 or not. If not, so you go to this decision. Otherwise, you check for another one, which is greater than less than 1000 or greater. So if it less, and then you go to this, and otherwise you go to this one. So see, 1 step, 2 step, and 3 step. It's not like one time compare everything is decide. So you have to do this way. Okay. Right, I think that's it. I don't want to go and further discuss on this. I think this part you can look for yourself from the answer I will be posting right after this tutorial, this review class. Okay, any question you want to ask about this exercise number 4? Question? So if there is no question, so the next question. If you have question, you can still ask, and then probably I can attend to your question while I setting up this one. Internet is very slow. Huh? Can open up from the e-learning. Oh, what happened? Huh? Try again. Okay. Question 2, right? Question 2. Let me share the this question. If you don't have, you can read lah. So question number 1, we already discussed. Question number 2 is we discuss now. It says here a light sensor generates an output voltage between 0.5 and 4.0 volt. You are tasked with designing a system to process the signal using 12-bit ADC with an input range of 0 volt to 3.3 volt. So the first question asked is about resolution. The resolution of the ADC. There's so many ways to calculate the resolution of ADC. I think last time also, just now also we do some resolution calculation by the formula, right? But I will show you the simplest way how to do this calculation of the resolution. if you understand what is the resolution or step, how many steps inside the ADC, so it'll be easy for you to do the calculation. Okay, let me see. You can see this. Already prepared this one. Exercise number 2, ADC, light sensor output is 0.5 to 4.0. Okay. So for you to calculate the ADC resolution, just need to use this formula. ADC voltage range divided by 2 to the power of n, where n is basically the ADC input bit resolution. So if you calculate from here, so ADC range basically, because this one is 3.3 volts, so you just calculate by 3.3 minus 0, starting from 0. So, and then over the 2, the 12 is the resolution bit, resolution of the ADC. And the answer is, you get here is 0.00806, 0.000806 volt per step. Okay, so if you can understand from 0, 3.3 volt, zero to 3.3 volt, right? So you have a total of 4,096 steps, which determine the resolution. Right. Every step is equal to 0.006. Right. This is a vola. Okay, per step. So you have 4,096 steps. This is your ADC. Okay. So this means if we have less step, for example, 2046, 2043, 248, 2048, half of this, right? If we have half of this, so what do you expect the resolution will be? The step resolution will be? Question. Must be answered this one so that you can understand. What do you think the resolution will be? Is it smaller or is it greater? Or value? This one I think is small enough, 0.008. Meaning that any change of the input signal of this value, so it will be detected, it will be converted. Okay. Kalau kita dapat lower resolution, for example, this is what, how many bit? This is 10 bit. What do you think this value will be? Yeah, greater volt per step, right? Greater volt per step, so meaning that it's not precise, it's not accurate, it's less accurate. Okay, so you have to understand, you have to get that kind of understanding so that you don't have to remember all of this formula. Right. Okay, so if you understand that, so it's easy for you to calculate the resolution of the ADC or the step resolution. No? Okay, good. Next, the second question. For what? Determine the gain and offset. So like again, if you look at the question, the voltage start at 0.5 and then maximum is 4.0. So certainly we are not going to use any of non-inverting or inverting amplifier. We are going to use what? We are going to use inverting amplifier. Okay. So when deal with the inverting amplifier, there will be an offset voltage and also gain. Right. So this is what you are asked here. Determine the gain and offset voltage. Go ahead for the op-amp to scale the sensor. Scale the sensor signal to the ADC. Scale the sensor signal to the ADC range, meaning that we have to want to use full use of the ADC range. Okay. So the way to calculate is just like this. Gain is actually ADC range divided by the input signal range. So ADC range is 3.3 minus 0 or 3.3 volt lah. And then the range of the signal is basically maximum minus minimum. 4.0 volt minus 0.5 volt. Then equal to 3.3 divided by 3.5. And then you get this gain. For gain for your differential amplifier. Okay, if you later want to calculate the RFRI, is up to you lah, you can calculate. But this is the gain supposed to be. Okay, and then the offset to shift the 0.5 to the 0 volt for the our ADC, basically we use this. This is a different way to calculate. The other one we previously we calculate differently, right? So this one is we just use negative 0.5 volt, the minimum voltage, time the gain. So again, you already calculated here. So when you time this one, so you get this voltage. So this is the offset. V offset voltage. Okay, the offset voltage is useful for your calculation of the your amplifier output. Okay. All right. So then the next question asks here, number 3, if the sensor output is 3.0. Now we have calculated all the gain and the shift. Now they ask, okay, the voltage from the sensor can be from 0.4 until 0.5. 0.5 to 4.0, right? So 3.0 is in between of that range. So 3.0 is in between of that range. So it asks what is the op-amp output and what also the ADC digital value. So you have to understand this one. If you don't understand, so it will be difficult for you to calculate. Op-amp output is just the output of the signal conditioning, the op-amp. So V condition, we call it V condition, which is equal to V sensor. So V that is coming from the sensor. Of course, for going through the signal conditioning, going to your differential amplifier, you will time the gain, right? Time the gain. So you get the output, right? But you have to plus also the offset because we are shifting it from the actual value to the 0. We just calculate that this is the V offset. So the result will be 3.0 is the V sensor that point at that time, 3.0 time the gain, okay, and then plus this offset is negative, right? Kalau positive lah. If this case is negative. So negative meaning that you have to minus lah, plus time minus ni akan dapat minus lah. So you will get the result of this 2.37357. This is the output of your differential amplifier ataupun SC lah, signal conditioning. Not yet the ADC, because output here, then go to the ADC. So then we calculate the ADC digital output. So this is the voltage that we get, and then we have to divide by the ADC resolution, which is this one. So you get the 2924 step, right? 2924 step. Ataupun this is the value of the step, so you have to calculate into digital. This one. So, okay. You have to do the calculation into digital, but this is actually 2924 step. Okay. All right. So, any question so far? We come to the last part of the question. This is the review question. So, you should be asking a lot of questions then, because we're almost done. The last part is basically just the question for your understanding. It's just a question for your comprehension of this thing, of this ADC. So what is the trade-off of using 12-bit ADC instead of a 10-bit ADC? Always the same. 12-bit ADC, of course, is higher resolution. You have 4096 level. Okay, you have 4906 step. That allow more precise measurement and as compared to 10. 10-bit lah, 10-bit lagi less kan. Then it's useful for low amplitude or high precision signal. Kalau kita nak measure some input voltage untuk high precision, so it's very good to use higher resolution. But what's the drawback? Higher resolution increase the ADC conversion time. Kalau you nak cepat, tak boleh lah. So you got to use a lower bit resolution. But for this higher, of course, it will require longer time. For example, kalau you ingat tadi kita guna SAR, the most famous one. If you want to convert more bits, so you have to use more clock. You have to clock. Kalau 8 bit, 8 clock. Kalau 12 bit, 12 clocks that you have to give it. So meaning that every clock is time. So there will be more time to spend there before the conversion is over. Okay, and then the greater bit depth require more memory. So kalau you nak more banyak bits, so you have to store this value into a lot of memory. So you're gonna waste a lot of memory, yeah? Not waste lah. You have to use more memory. More memory will cost you more cost, more money, okay, and more material over there. So that's a drawback. That's the way to think about that. All right. So that's it. Any question? I think over 3 already. If any question, this is time to ask before we end this session. Question 3, yeah? Let me get the question again. You're asking question 3, use gain time the V2 minus V1 instead, same as R. Yeah? This is the same. You can use that one. Any other question?
Doktor, nanti bagi formula ke?
formula, some of the formula, yes, will be given in the back of the paper lah. So you have to check, you know. Kalau you tak check pun, it's no use juga. There will be some formula related on the back of your exam sheet, exam question. Some students actually they don't check, they get panic and then they check. There's one cheat sheet lah inside, and baru belakang tu you cannot find out which one the formula is you are looking for. I would advise you to repeat whatever I've already discussed with you today again and again so that you get familiar. So even though you know how to do it, but you're not fast, so you will end up that you spend more time on one question, right? So you have to exercise, do it again and again so that you can understand. Then you do it very fast. So you can focus on the difficult question, more difficult question. This kind of question is very easy, so you can do it very fast. Okay, any question, any more question? If there's no questions, we'll end the session now. And then you're gonna have to wait for Dr. Tena session and also Dr. Iman session. Okay. I'm gonna start recording now. So if there is no more question, I will end this session now. I wish you all good luck and then get prepared and then try to study and then try to repeat the exercise and then come to the exam hall with confident lah. You can answer all the questions. All right, thank you very much. Good luck, guys.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Welcome.
Thank you, Doctor.